welcome guys. So in this video, let's talk about Mellin transformation. So this video is the first lecture of Mellin transformation, and we will just talk about definition and see some examples. Okay. So this is my own notes. Okay. So Mellin transformation, let's say you have a real number, a real function from real number to real number, and you can define the Mellin transformation. Will be f of x times x to the s minus 1 dx, and do the integral from 0 to infinity. So the Mellin transformation of f will be function of s. Okay, and MFS is called Mellin transformation. Okay. So the first example is obviously easy one, right? You put exponential negative x, so exponential negative x s minus 1 dx 0 to infinity. So by definition, this is a gamma function, right? By definition. So if you haven't seen a gamma function, you can go to my channel. I will put go to my video list. I will put in here. Okay, and f of x equals to the second example. Also common is that you can define f of x to be x to a from x 0 1 0 to 1 and else is 0. So put in here and then you get 1 over a plus s. Okay, this is very easy, right? It's just an integral polynomial. And why we put 1 here, right? If we put infinity here, then this integral will blows up. Okay. And the second one, the third one is exponential negative px. So just change this negative x to negative px. So exponential px here. So this is same as gamma function, right? If you do the change of variable, you define y equals to px. So it's exponential negative y. Let's say so x is y divided by p, right? So y to s minus 1, p to s minus 1. And the dx can be changed to dy divided by p. So it's here. So it's 1 over ps to the exponential 0 to infinity, exponential negative y to s minus 1 dy. So this is a gamma s divided by ps. P to s. Okay. So this is also a famous integral. Okay. So these three are the common Mellin transformation. And then we will talk about the next two. Okay. So the next two is the interesting one, especially this number 4. Okay, so maybe we see number 5 first, because number 5 is common. It's also similar to these three. So how about f equals exponential negative x to a p? Okay, so let's say p must greater than 0. So your Mellin transformation of f will be 0 to infinity exponential negative xp x to s minus 1 dx. Okay, so the common, the easy way, right? The straightforward change of variable will be x to a p defined to be y. So your x will be 1 to the power 1 over p, so, and then you do dx, right? Dx equals to 1 over p, y to 1 over p minus 1 dy. Okay, so this one is exponential negative y, and y to the, right, so y is here, right? Y is xp, so let's see what's going on. Oh, okay, yeah. So this x to s minus 1 is basically s divided by 1. S minus 1 divided by p, and then times this dx. So dx is 1 over p times y to the 1 over p minus 1 dy. So it's this. And then combine these two, we get 1 over p 0 to infinity summation negative y to x minus divided by p minus 1 dy. So it's 1 over p gamma x divided by p. Okay. And by definition, something times this the same is basically, so yeah, this is the answer. So one common example is s equals to 1. We get 0 to infinity exponential x to a p dx equals to 1 over p gamma 1 over p. This size by definition, this is 1 over gamma 1 plus 1 over p. Yeah, so this one and this one and this one, basically three of them can be used things as a generalization of gamma function. Okay, and number 4 is really important that I think it's somehow like showing the statistical physics and the string theory. So the number 4 is and the analytic number theory. So we will talk about now. So let's talk about number 4. So number 4 is the Mellin transformation of 1 divided by exponential x minus 1. Okay, so minus 1 is not only exponent. Okay, so this is the integral of this, right? S to s is exponential x minus 1 dx. So we can times the exponential negative x from the denominator and the numerator. So the numerator becomes exponential negative x to s minus 1 dx. And what's the denominator, right? Denominator is 1 minus exponential negative x. And then we can use the 1 over 1 minus x will be 1 plus x squared plus x cubed. So this can be this numerator, denominator can be written as this. So basically, this is x to exponential minus nx, n from 0 to infinity. So it's s to s exponential minus n plus 1x dx, n from 0 to infinity. So it's n from 0 to infinity integral x to s minus 1 exponential negative n plus 1x dx. So this is the gamma function, right? So it's gamma s divided by n plus 1 to the power s. And n is from 0, so I can dummy variable, I can change it from 1. So I get gamma of s divided by n to s. So if you pull out the gamma of s, and you get n from 1 to infinity, 1 over n over 1 over n to the s, and this is famous Riemann zeta function. Okay, so the famous result is that this integral, okay, showing the statistical physics, especially for s equals to 4, I think s equals to 4. Showing basically it's gamma s times zeta s. It's the gamma function and the product of gamma function this Riemann zeta function. Okay, so this is the first lecture of Mellin transformation, and the second lecture we will talk about inverse Mellin transformation and the Perron's formula, and prove that inverse Mellin and the Mellin actually are really inverse to each other. So Mellin transformation can be viewed as like the small. It should be powerful than Fourier transformation and Laplace transformation, but it's not very common in the. I think it's not very common in the literature or in the like college course. So I mean, I built this video just for fun. Okay, so hope you guys subscribe to my channel. Okay, I will see you guys in the next videos.